Okay, before we finish up chapter 7 completely and we tie it all together to try to figure out how we can determine what kind of reaction is preferred, a substitution or an elimination, and then to choose between an a 1-type reaction versus a 2-type reaction, we have to come across this concept of polarizability of atoms. You might or might not remember that in general chemistry you talked about atoms and their polarizability. That is, are the atoms able to push their weight or to have the majority of their electrons move in one direction so that they can target a specific thing? Meaning, can they move their electrons from one side to another? The more electrons that an atom has, the more ability that those electrons can shift towards a positive charge. Shifting the electrons towards a positive charge is what we refer to as polarizability. So we would have seen this concept in general chemistry. We also kind of saw this concept when we talked about intermolecular forces on the first chapter of this class. And that is when we looked at two different atoms and we said these two atoms both have electrons that are surrounding each one of those atoms. But as the atoms come close together, something happens, right? The center of the atom is positively charged, and the outside of the atoms are where all the electrons are. Well, if the two atoms are coming in close proximity to each other, the electrons are going to prefer to be right in the middle of those two atoms. Those electrons are going to shift right to what we call the sweet spot. The sweet spot is going to be where the electrons are being able to enjoy the positive charge between two of those atoms. That force, or the ability to be able to do that, is what we refer to as the London forces or the dispersion forces. And so that whole concept holds throughout all of chemistry. And it shows up in the polarizability of atoms. Why is that particularly important in organic chemistry? Well, very shortly, we're going to have to identify the difference between bases and nucleophiles. So far, we know that bases and nucleophiles have a whole lot in common. We know that bases normally have a negative charge or a partial negative charge. So mainly, they have to have some electrons that can do some attacking. Well, what is a nucleophile? Well, nucleophile is exactly the same thing. A nucleophile is a negative charge or a partial negative charge in which electrons do some kind of attacking. So the question is, then a nucleophile and a base are exactly the same thing? And the answer is absolutely not. The difference between these two definitions is what kind of attacking do nucleophiles and do bases do? Nucleophiles attack at the alpha center. So nucleophiles exclusively at the alpha site. Okay? Where is the alpha site? The alpha site is the carbon to which a leaving group is attached. So if we have our specific substrate and we have a leaving group, then this carbon right here is our alpha site. It turns out that bases, on the other hand, they do attacking, but the attacking that they do is specifically of a proton. So bases attack exclusively hydrogens. Now, where are the hydrogens located that bases can attack? Well, bases can attack any hydrogen that is partially positive. Where do we find partially positive hydrogens? Most of our partially positive hydrogens are hydrogens that are directly attached to very electronegative atoms. And so hydrogens that are partially positive are things that are attached to electronegative atoms. So a hydrogen attached to a chlorine is a very positive hydrogen, and we know that because this structure right here is actually an acid and can very easily have that proton removed. We have other structures in which we have a hydrogen that might be attached to an electronegative like an oxygen, and a base can remove that hydrogen if what it leaves behind is more stable than that which took the hydrogen to begin with. This is area. We did this in chapter 3. We could determine whether the hydrogen could be removed or not removed based upon using area. And if we ended up with a product that was more stable than the starting material, we determined that the reaction could happen. That was the definition of a base. Well, it turns out that substitution reactions, or just stealing hydrogens from things that are more electronegative, is not the only kind of reaction that we can have. And in this chapter, we started learning that we could take hydrogens, even from carbon, if it produced a more stable double bond. That means that the negative charge is not going to create a negative charge on the carbon itself, but it is taking a beta hydrogen that is then going to push out a leaving group, which is going to be more stable than a negative charge. I'm still going to say that you start with a negative charge, you end with a negative charge. You determine if the reaction is going to occur if the negative charge that results after the reaction is more stable than the negative charge that you started with. The problem is that a direct substitution or a direct removal of a hydrogen on an electronegative atom to create a negative charge is not the only kind of reaction that we can have. We can actually have a reaction in which a hydrogen can be taken from the beta position. So as we were doing in our previous video, if we have a leaving group and we have hydrogens that are beta to this is my alpha position, this is my beta position, then I know that a base, as long as the hydrogen and the bromine are in the same plane, so let's rotate this so that my hydrogen is in the same plane as my bromine. Now my base can grab my hydrogen and it can force the bromine to leave. And that would give me this compound. In addition, I could do the same thing. I could grab a base here and I could pull this hydrogen and I could create this compound right there. So both of those compounds are possible based upon a base removing a hydrogen that is beta. So a hydrogen that is beta to a leaving group must be partially positive, and in fact it is. To take that hydrogen identifies you as a base. So the question now becomes, if the only difference is what they do, how come some things are better bases than they are nucleophiles? And how come some things are better nucleophiles than they are bases? And the ability to be able to distinguish between the two has something to do with the alpha site and has something to do with the ability of the atom to polarize itself. Atoms that can polarize their negative charge can direct that negative charge into more of a point. It can put all of the electrons in one direction, making that negative charge stronger than it would be otherwise. So let's see if I can identify some differences in bases and how we can determine whether something is a base or a nucleophile. In our next video, we're going to have to be able to separate, and we're going to have to be able to identify what is a strong base but a weak nucleophile, and what is a strong nucleophile but a weak base. And the answer to that is a strong base is something that is very negative, so a negative charge. So it really wants to get a hydrogen, but it cannot attack at the alpha site. Because if it did attack at the alpha site, it would be a nucleophile. And if I want it to be a weak nucleophile but a strong base, I need it to be very negatively charged, so it's looking for a partial positive. But I'm going to handicap it. I'm going to make it impossible for him to attack the alpha site. And what I do is I realize that the hydrogens that are surrounding this compound, if this is my alpha site, I have hydrogens, and these hydrogens are farther away from the center of the action. So they're more available, they're more accessible. So something that is negatively charged but can't attack an alpha site is going to be something that's really, really big. So things that have a negative charge but tend to be really, really large is the definition of something that is a strong base but a weak nucleophile. And in this chapter, they identify several different kinds of structures that have negative charges that are too large to be nucleophiles. They can't attack the alpha site. So therefore, they can act as bases, but they don't act as nucleophiles very easily. So two examples of that are DBN and DBU. I'm only going to draw a structure of one of these, but they're very similar. Roughly something like that. The point is that it's a very, very large structure. Another typical is LDA, which we're going to be introduced to, and that has a nitrogen, where the ammonia comes from, and it has a diisopropyl. It has a negative charge, and it has a lithium, which is positive charge, which is the counter ion. So lithium diisopropylamine is a very large negative charge nucleophile, base, which is very, very strong because it has a negative charge, but it's too large to actually be a nucleophile. There is one exception to this rule, that even though it is really small, it's not very good at being a nucleophile. And the reason why is because it's not polarizable, and that is sodium hydride. So sodium hydride has a positive charge here, has a negative charge here, and you're like, well, that's about the smallest thing you could possibly find. Why is it not a good nucleophile? And the answer is because it only has 2 electrons, so this is not polarizable. So all of this brings us back to, how do I get a good nucleophile that isn't necessarily negatively charged? I have to find something that is not very negative because it's a weak base, but is very polarizable, is a strong nucleophile. What would something like that look like? It has to be something that has an atom that has many, many different electrons. For instance, if I look at this compound right here, I normally draw it with a lone pair of electrons and a negative charge, but we know that all halogens have 8 electrons in its outer shell. How many total electrons does iodide have? It turns out that iodide has 126 electrons. It has a negative charge because it has an excess electron, but it has a lot of electrons. And so iodide, which is really, really, really big, as the iodide gets close to a positive charge, what's going to happen to all of the electrons that are surrounding that iodide? All of those electrons are going to actually form a cloud right here. The closer they are to the positive charge, the more pointed that electron gets. And as it turns out, that ability to be able to focus all of its electrons so that it can be like a knife and be able to attack that positive charge is the definition of polarizability. So we're going to identify in our very next video a whole bunch of different things that aren't very good bases, because an iodide with a negative charge is pretty darn stable. It doesn't want to go around stealing hydrogens, but nonetheless, it is a strong nucleophile, and it is a strong nucleophile for its ability to be polarizable. So it turns out that iodide, bromine, even to a certain extent chlorine, are not very good bases, but are good nucleophiles. Other examples of things that are not very good bases, but are polarizable, is sulfur. It turns out that sulfur, even if it is not negatively charged, it's not going to be a very good base if it's not negatively charged. It's neutral. But because sulfur has a second row of electrons that first row, nitrogen, oxygen, and carbon, do not have, it has excess electrons, which it can point into the shape of a knife in order to be nucleophilic. So sulfur is a good nucleophile, but it is a very bad base. And all of this is due to the fact of polarizability. So on the very next video, we are going to talk about how to put all of this together, how to determine whether something is a strong base or a strong nucleophile, and how to determine whether something is a weak nucleophile or a weak base.